Hi class, this is the online lecture for Thursday, April 6th. I'm sorry, but I've had some meetings that I've been required to attend this morning, so I'm going to have to cancel the in-class lecture today, but I have prepared this lecture. Should be about 45 minutes for you to watch, and please come prepared to class next week to ask me some questions about mass wasting, as this material will be on your final exam. Or your midterm exam, as well as the quiz, number 6, next week. Just to review, the slowest, remember, mass movements are any downslope movement of material. And we have types of mass movements that range from very slow, such as creep, and solifluction, which is the freeze-thaw method where the soil expands, then moves down slope, to slightly faster as we move to the right, which we call slumping, to even faster than that, where we have mud flows, debris flows, and lahars. Remember, lahars are debris flows that occur on the sides of volcanoes. Finally, we have rock avalanches or snow avalanches that would be the fastest. Now, in addition to a material moving as a fluid, which we would call a flow, we also have slides, such as rock slides, which can be either translational or rotational. And finally, we have rock falls, where rocks are literally falling out of the air. So I've got a couple videos I'd like to show you of both an example of a rock fall and what I would call either a high-speed slump or a rotational slide from La Conchita towards Santa Barbara.
It's coming down. Oh my God. Hey! Hey! I want to go home. Hey! Come here! It's cold! I'm going to go get the kid!
The first video was definitely a rock fall. That was a rock fall that occurred in Taiwan. The second video I would call a slump, pretty fast and moving like a fluid down the slope. That'd be more like a rotational slump, probably. And then the third video was definitely a moving massive rock down the side of a volcano, so we call that a lahar. And just to quickly fill in these others, we have creep as being the slowest downslope movement. Not very exciting in terms of YouTube. An avalanche, which is the fastest type of flowing mass wasting. And then we have our rock and landslides. And landslides that are fast moving, but really moving more as a coherent block. So that concludes our quick review of what we went over on Tuesday. And just a reminder, problem set number 3 is due next Thursday at midnight. It is posted in Moodle. I call it Los Angeles Against the Mountains. And it's all about the history of debris flows, such as this one that occurred up in La Cañada, about 20 miles away, of landslides in Los Angeles, and how we try to prevent them, primarily by the use of what we call debris dams along the front of the San Gabriel Mountains. I'd like to review the causes of mass wasting. There are two primary causes. The first cause of mass wasting would be due to gravity. Basically, anything on Earth is being pulled down by gravity, and if it can't be held in place, it slides down. So mass wasting, downslope movement of material, all fundamentally controlled by gravity. The second main cause is what I'm going to term a weakened substrate. Now, substrate is just the material, typically earth or soil or rock, that lies beneath the slope. And obviously, if it's weak, it's going to be more prone to failure and sliding down the mountain. If it's very strong, it's probably not going to slide down the mountain. So let's talk a little bit about those two different things. Gravity, of course, is the force that pushes down towards the surface of the Earth. So we'll call this gravity. I'm going to change the color here, and I'm going to make my slope. And let's have a slope here. So whenever gravity is pushing down, it gets divided up into two components. It gets divided up into a component that is perpendicular to the Earth's surface, which we call the normal force, or the normal component of gravity. It also, part of gravity, you can see because gravity is hitting the slope. Gravity is hitting the slope at actually an angle. If we go downslope, the force of gravity that is parallel to the surface is called the shear force. Now, there is a third force that is not being controlled by gravity that is actually the resistant force on the surface, which is the force that's pushing back against the shear force. So, in a theoretical condition, the shear force, downslope force, is going to be equal and opposite to the resistant force. Now, if the shear force exceeds the resistant force, and I should note, resistant force is really just a fancy way of saying it's the friction or the strength of the rock on the surface, because the resistant force is fundamentally controlled by friction. If the shear force is greater than the resistant force, then failure occurs. So this is the reason gravity causes landslides. If you have a flat landscape and gravity is pushing down, again we're going to call this G, then let's say we have a block on the surface. 100% of gravity is going to be this normal force. And you can see that none of the gravitational force is causing the block to slide. So gravity is all normal and you get no movement. That's why we don't have to worry about landslides if we're on a flat slope. Equals no landslides. However, if we've got a steep slope and we've got a block on our steep slope, gravity is still moving in the same way. And look, most of the gravity is pushing directly down that slope. Most of gravity is mostly shear, and ultimately this block is not going to be able to stay in place and is going to be moved down the slope. So this is just a fancy way of saying steeper slopes are more prone to failure because they're feeling more of the effect of gravity. So other than being pushed downhill, which is the effect of gravity, the other thing that causes landslides is a weakened substrate. And there are 4 ways to produce a weakened substrate. One is to have a thick soil. Soil, remember, is what? It's weathered bedrock, which means it's bedrock that has been disintegrated or destroyed either through physical or chemical processes, making it weak. If it's weak, it's more prone to failure. A second way to form a weakened substrate is to actually have weaknesses in the bedrock, such as fracturing of bedrock. If your rock is not solid, it's weaker, it's more prone to failure. A third way to weaken the substrate is to fill it up with water. We call this the effect of pore pressure, which is just a fancy way of saying add water. And the fourth way to weaken substrate is to remove vegetation, or have a lack of vegetation. Because vegetation essentially acts like rebar. Why do you put rebar in concrete? To strengthen it. That metal actually holds the concrete together. Well, roots do the same thing for a soil surface. Roots hold the soil together. Remove the roots, you're more apt to have failure. I think the soil thickness is pretty self-explanatory. The thicker the soil, the thicker the weathered bedrock, the more apt for failure it is. Also, if you have a lot of fractures, it's going to be weaker, but pore pressure is a little bit harder to understand. Here, this is a case for sediment or grains of sand that have no fluid between them. You can see in most cases, all of these grains are actually touching, and they're very compacted. Well, you add water between those grains. That water actually, as a fluid, it exerts a force on those grains. It pushes the grains apart. Well, if the grains are no longer together and they're apart, they're more apt to move, and when they move, they are much weaker. So this pore fluid pressure is the effect of water in the pore space that literally weakens the sediment. So if you're at the beach, make a sandcastle. The sandcastle will stand up, and then take a glass of water and slowly pour it on one part of that sandcastle. And you'll notice that it's not really destroying it due to the physical processes, but the water soaks into the sand and the sandcastle essentially melts away. This is because that water is is basically pushing the grains apart. When they're being pushed apart, they no longer have any cohesion, there's no friction between them, and it weakens your substrate, which can also cause slope failure. And finally, I'll add that the lack of vegetation, again, is the rebar example. So let's move on to, now that we know what causes mass wasting, well, that's what essentially happens to the surface that makes it want to fail, but there has to be a trigger. Our slopes around us aren't all landsliding. And why not? Well, it's these triggers that actually overcome the resistance stress that cause the shear stress to exceed the resistance stress that cause these slopes to failure. There are three main types of triggers that I want to review. The first, living in California, you should be familiar with this, is shaking. Usually the result of earthquakes. Obviously, if you've ever lived through an earthquake, you know that it shakes everything up. Bookshelves come down in your house. Lamps tip over. It does the same thing on slopes. It causes slopes to, you shake them up, and they tend to fall down. The most recent large earthquake to hit Southern California was on January 17th, 1994. It occurred at 4:31 a.m. This was a good thing because you'll notice this was the old parking lot G3 on CSUN campus. That shaking caused essentially these columns to collapse, which caused the whole parking lot. But because it was at 4:30 a.m., there were no classes going on, there was nobody in there, nobody died. Imagine if that happened at 8:30 or 9 on a Tuesday or Thursday morning. It would be not such a good thing. Same earthquake caused the 14-5 interchange to fall down. Interestingly, this same structure fell down during the 1971 San Fernando earthquake. And my prediction is that the next time a big earthquake hits this area, despite all of the reinforcement that has occurred on that freeway overchange, it may come down as well, again, in a future earthquake, because high, tall bridges just do not stand up to shaking very well. But certainly, a lot of the damage that occurs during earthquakes is caused by landslides that are triggered by those earthquakes. But other things other than we have landslides even when we don't have earthquakes. For example, another thing that can trigger mass wasting is the changing load on a slope, the changing weight on a slope. This can occur in a couple of different ways. One way it can do by over-irrigation, by watering a slope. You add water to a slope, you're adding weight to that slope, and there's a lot of lawsuits in the Los Angeles area for people that live at the bottom of hills. If someone's slope comes down into their house, they blame the homeowner above them for over-irrigating. So due to, let's say, overwatering or building on top of a slope. Now, a second trigger for mass wasting is just a change. So 3 would be a change in the slope strength. And there are a number of different ways to change slope strength. One way is by undercutting, or taking out the base of a slope. For example, here you've got a cliff face that used to be vertical. When this water eroded the base of the cliff, obviously there's nothing holding up this upper block, and so you cause a rock fall in that manner. So undercutting is one way. There are a couple other ways I want to review. Take a look at this slope. Notice it's nicely vegetated, it's got a nice grade on it, and it seems pretty stable. But what happens when you want to build a platform for a house up here? Well, what do? First of all, you probably put in a lot of artificial fill, which causes you increase the weight or increase the load on that slope. You also remove the vegetation, which is acting to weaken the slope. And then what do? Well, you have your nice little house on the hill, and so you want to have a nice yard outside. So you irrigate, which also acts to increase the load on the slope. And so these three things, basically, what you've done, you've changed the water content. You've changed the water content, increased the water content, increasing the pore pressure. You have also removed vegetation. So let me go to another. So increased water content, removed vegetation, increased the load, all things that act to change the strength of your slope. And a fourth thing that I haven't discussed is that actually weathering or soil creation creates a thicker soil, but weathering also can change strength of your slope. So here's just another example. You don't have to have humans that go in and cause the vegetation. Again, this is how fires are going to affect landslides. Fires act to remove the vegetation, fundamentally weakening the substrate, increasing the chance for landslides. So the take-home message: weathering and fragmentation weaken slope materials and make them more susceptible to mass movement. Failure occurs when downslope pull exceeds resistance force due to shocks, change in slope angles and strength, changing water content, and changing the slope support. So finally, if this is how landslides occur, these are the triggers. We can either A, try to avoid the triggers, but sometimes that's inevitable. If there's a lot of rain, you can't avoid adding more water to the slope. But this is when we call in our friends, the engineers, to help us mitigate these slope hazards. What can we do to prevent slope failures? As a geologist, we can go observe where these slope failures might be. First of all, what kind of slope failure is this? This would be a rotational slump, right? You see the headscarp up here, you see the toe, there's evidence for hummocky or irregular land surface, you see tilted power lines that may be the effect of either the slump or slope creek. You see cracked foundations. What can we do about that? Well, we can try to prevent these from happening in the first place. So, how do you do this? One way is to revegetate. Obviously, if you take away vegetation, it weakens it. If you put back the vegetation, that helps too. And you should all have seen examples of this. I know that you all drive on the freeway, and you notice that along the edges of the freeways, whenever you go into an underpass, there's these nicely manicured, basically plants that are planted. Is this a way of, spending our tax dollars to make it look pretty for us? No, it's a way of keeping the slope strong. A second way is to actually regrade. Or make the slope so it's not quite at such a high angle, so gravity's not having as much of an influence. I'm going to write down these different ways, and I'm going to then show you examples. The third way is to dewater or reduce the surface runoff. Reduce runoff. The fourth way would actually be to stabilize slope. And you can do that by either putting in bolts, such as these shown over here, or putting in rock walls, and essentially try to prevent erosion of that slope and prevent undercutting. So I'd like to quickly walk you through these things. Obviously, revegetation, you're adding rebar and roots back into that slope, and will stabilize the slope. Another way to prevent these mass movements is by this process of regrading. So what have they done here? The slope has actually been terraced. It's been terraced for a couple reasons. One, you put a nice flat surface, so if any of this slides down, it'll get caught on that flat surface. Plus, you've created more space back here for these homes to be in. And so they catch debris, and it removes some of the places that you can actually load the slope. So you've ultimately removed some material off that slope. So you've decreased the load, again, another important factor in mass wasting. So regrading, and then changing the drainage. Drainage can be changed by actually putting in drains, or putting in canals, and basically changing the drainage through putting in drains and water catchments. Again, if any of you are driving along the freeway and you look up at the side of a road cut, you'll see big channels that are cut across that collect that rainwater, so the rainwater doesn't focus on the slope, it actually gets removed from the slope. We can also try to eliminate undercutting. Here, this river would flow to undercut the base of this channel. A lot of times engineers will put in riprap, which are large boulders that go along the base of a slope that prevent erosion, and that prevents undercutting, which is another major factor in slope failures. Or you can build walls that essentially collect or trap debris behind them. They also act to strengthen the slope. You can see here the slope went down to the bottom, but if this fills up with material, you've actually reduced the slope to the top of that wall. And as we know, slope is directly proportional to the effect of gravity. Or you can simply bolt the wall in place. Again, you add a bunch of bolts to your wall, it holds it together better. So I hope you've gotten something out of this lecture. I want you to think about the different aspects of mass wasting. The take-home message here, various features of the landscape may help geologists to identify the unstable slopes. The engineers can repair those slopes through a variety of techniques. So finally, what do you need to know from this lecture? Well, you should certainly know the different types or classes of mass wasting. Flow, slide, fall, avalanche, creep. I would add a couple of those too. Avalanche and creep. The factors that contribute to mass wasting, the triggers for mass wasting, and what can be done about it. I probably won't, well, half of next week's quiz number 6 will be on mass wasting, and I will add to our Padlet page some questions that I think you should know how to answer. So use your book, review Chapter 13, and hopefully this will help you, and I will see you next Tuesday. And again, sorry that I had to cancel class. Thanks, and have a good weekend.